So let us start with the solution of the questions of the practice set for the subject design and analysis of algorithms. The first question says that define B tree and its properties. Construct B tree of order of 5 for the following three set of keys. So we have to construct the B tree for these three sets of keys. So let us start with the definition of the B tree. A B tree of order M is an M-way search tree where each node can have up to M children and M minus 1 keys. It generalizes the binary search tree by allowing nodes to contain multiple keys and children. B trees are widely used in databases and file systems because they reduce disk input-output operations by keeping data balanced and sorted. The properties of the B tree are the essential properties that define a B tree of order M are: first property is node capacity, which says that each node can hold at most M minus 1 keys and M children. Each node except the root node and leaf node must have at least floor of M by 2 children. The root must have at least 2 children if it is not a leaf. All leaf nodes appear at the same level, ensuring balance. Keys within a node are sorted in sorted order. Subtrees between keys contain values within the key ranges. Searching within a node is done using binary search. Overall search, insertion, and deletion operations take big O of log n time. So we have to construct the B tree of order of 5 for these three set of keys. So the order value of M is given as 5, order is given as 5. So as the value of M is 5, order is 5. Each node can have max 4 keys and minimum 2 keys except the root node as per the properties of the B tree. Each internal node can have 3 to 5 children. So let us solve the first part. In the first set of part, we have been given the keys 1, 2, 3, 4 up to 25. They are already in sorted order. Start with the root. We have to first of all add the element sequentially, that is 1, 2, 3, 4, because the order M is 5. In each node can have maximum number of 4 keys. So when we have added these 4 keys 1, 2, 3, 4, maximum capacity has reached. That's why when we are going to insert the next key 5, it will result in a split operation. And when we are doing split operation, the middle splitting, the root will be the middle node, that is in this case root becomes 3, and the children will become left child will be where left child contains the keys 1, 2, and the right child will contain the keys 4, 5. So in this manner we continue to insert all the keys up to 25, and this will result in a B tree like this. So this is the solution, or you can say B tree of order of 5 for the first set of keys. Similarly, let us solve the second part. So in the second part, we have been given the keys as 50, 20, 70, 10 up to 1, 6. But in this case, unlike in first part where the keys were already sorted, in this case, the keys are not sorted. But we have to draw the B tree of order 5, that is value of M is 5. So let us start. Step 1, rule for B tree of order M says that each node can hold up to 4 keys, as I have earlier told you. Each node must have at least floor of M by 2 minus 1, that is 2 keys except root node. Splitting occurs when a node contains more than exceeds 4 keys. The middle key moves up and become the root node. So first of all, we insert the keys sequentially. First 4 keys we insert 50, 20, 70, and 10. And automatically these will be sorted in ascending order 10, 20, 50, 70. Then we are going to insert 30. When we are going to insert the fifth key whose value is 30, split operation will take place. And again in sorted order, 30 will become the root node, and 10 and 20 will become the left node, and 50 and 70 will become the right node. So in this next element to be inserted is, after inserting 30, next element to be inserted is 60. Clear? Next element to be inserted is 60. So it goes to the right child because the right child value 60 is greater than 30. That's why it goes to the right child, and right child already contains the element 50, 70. So right child will now contain 50, 60, 70, right? Then the next key we are going to insert is the key 80. After 60, we are going to insert 80. Again, Again, because value 80 is greater than root node 30, it will again go to the right child, and the right child will now become 50, 60, 70, 80. Now, when we are going to the insert the next key after 80, the next key to be inserted is 5, but because already in the right child, 4 keys are there, but because value 5 is less than root node 30, it will go to the left child of 30. So left child will now become 5, 10, 20. Right. Next, uh, so this should be here. This result should be here. That is after inserting 5. Next, we have to insert 15. 16, 15 is also uh, less than 30 root node. So it will become, it will go to the left child 15. After 5, we have to insert 15. Na? After 5, we need to insert 15 because 15 is less than 30. It will go to the left child. So it will become 5, 10, 15, and 20. But now on in left child and right child, we have reached the maximum limit. That is, left child also contains 4 keys, right child also contains 4 keys. So next we are going to insert after 15, we are going to insert 25. So split operation will take place. 25. Next we are going to insert 25. So because overflow will occur, and we are going to insert 25, it will, because 25 is less than 30, it will be added in the left child, but in the left child overflow will occur here. Overflow will occur because each node can contains at most 4 keys. So when we are going to insert 25 here, split operation will take place at 15. Already root node was containing 30. Now it will contain also 15. So 15 comma 30, left child of 15, 30 will become 5, 10, and right will become 20, 25. Right. So this operation continues and will be finally reaching to construct this this B tree. So this is the solution to the second part of our problem. We have successfully constructed this B tree of order 5 for the second set of keys. Similar operation is applicable for the third set of keys, but unlike the part 1 and 2 where we were given the numerical keys, numbers, here we have been given alphabets. So we have to, there we were considering the ascending operation. In this case, we will be also sending operation, but alphabetically. Like A comes before B, B comes before C, like this. But the procedure for constructing the B tree will remain the same, and we will finally get this B tree in shape. So these are the steps shown, and finally we will get this B tree. Like you can easily draw by again following the properties and definition of the B tree. Right. So we have successfully solved our first question. Second question is, define AVL tree, explain its various rotations. Second question. Uh, for your convenience, again, in the first question, these steps have been shown how to construct a B tree, right? However, I have already given you the definition of B tree and its properties earlier. You can also follow these set of rules for constructing the B tree. So here the steps have been shown further in detail order for the first set of keys, then second set of keys, and the third set of keys, right? Now we would like to solve the second question. Second question says that define AVL tree, explain its various rotations. So an AVL tree is a self-balancing binary search tree where the height difference, also known as balance factor between the left and right subtrees of any node, is at most 1. To maintain this balance, AVL trees use 4 types of rotations. First rotation is known as LL, left left. Second, right right, RR rotation, LR, and RL rotation. These rotations restore balance in constant time while keeping the operations efficient. So first of all, we will be discussing the definition of the AVL tree. AVL tree was invented by Georgy Adelson Welsky and Evangeline Landis in 1962. According to the definition of AVL tree, balance factor is given by height of left subtree minus height of right subtree. And for every node, the balance factor should always be greater than -1 and less than +1 or equal to +1. The operations performed on AVL tree can be searching, inserting, and deletion operations, and all these operations run in big O of log n time because the tree height is kept minimal. Now we'll be discussing different types of rotations in AVL trees. Rotations are used when insertion or deletion causes imbalance. That is, when balance factor becomes less than -1 or greater than +1, then the imbalance occurs. So in that case, we have to do the rotations. There are four cases. First is LL rotation, that is also known as right rotation. The cause of LL rotation is insertion in the left subtree of the left child. So as you can see here, the root node is 30 and we want to add another node 20 because 20 is less than 30. 20 will be added to the left of 30. Again we are going to uh, add next element 10. Since value 10 is less than 20, so 10 will be added to the left of the node with value 20. But here the imbalance occurs because the balance factor becomes you can check here, balance is nothing but height. So balance factor height of left subtree is you can see here height is 1 2 and the right is 0. So 2 minus 0 is 2, so it becomes greater than +1. So it becomes greater than +1 and the imbalance will occur. That's why to fix this problem, we will performing a single right rotation. That's why, right. So we will rotate 30 to the right such a way 20 will become the root node like this. We will be rotating this 30 to right, right? 30 to the right of 20. So 20 will become the root node. 10 is already the left node. And after rotation 30, because we are performing the right rotation, 30 will come to the right side of the node 20, right? So this is how the LL rotation occurs. Similar is second rotation is known as RR rotation or left rotation. Why this rotation is what is the cause of this rotation? Because insertion in the right subtree of the right child. For example, see, first element is 10 and next element you want to add 20 because 20 is greater than 10. So 20 will be added to the right of 10. Then we are adding another element 30, next node 30. 30 is again greater than 20, will be adding 30 to the right of 20. But again here imbalance occurs because balance factor says that here height of the left subtree is 0 and right is 2. So 0 minus 2, according to this 0 minus 2, balance factor becomes -2 and balance factor becomes less than -1 because in this case -2 imbalance occurs. That's why we have to fix this by performing a left rotation. So we rotate this 10 element root node left such that 20 will become the root and 10 will be rotated to the left and will become the left child of 20 and 30 will remain the right child of 20. So we have to, in this case, we have performed one single left rotation and it is also known as RR rotation, right? Clear? And the third is the LR rotation, that is left right rotation causes insertion in the right subtree of the left child. For example, first node is 30, next we want to add 10 because 10 is less than 30. We will be adding 10 to the left of the node 30 and then we are going to add 20 because 20 is greater than 10. 20 will be added to the right node, 20 will be added as the right child of node 10, right? But again we will be computing here the uh, balance factor, that is balance factor formula is height of left subtree minus height of right subtree. Height of left subtree minus height of right subtree. As you can see here, because this is the height of left subtree, right? And height of left subtree is again 2. 2 minus 0 is +2. So again, balance factor violates the property of AVL tree. Imbalance occurs because balance factor should never be less than -1 and should never be greater than +1. So that's why the Imbalance again occurs in this case also. So the fix is to perform a left rotation of the left child. So we will perform the left rotation of the left child. Clear? So we will perform left rotation of the left child. So left rotation of the left child. So 10 will be rotated left, right? And right rotation on the root. Right rotation on the root. So 30 will be rotated to the right and 10 will be rotated to the left and 20 will obviously be the will become the root node, right? So this is known as LR rotation. Similar is the RL rotation, that is also known as right left rotation. In this case also the imbalance occurs because balance factor will be property will be violated, that is height of left subtree minus height of right subtree should never be less than -1 and should never be less than +1. So again, in this case, we will be performing a right rotation on the right child. That is, 30 will be rotated to the right and left rotation on the root. That is, 10 will be rotated to the left. So this will be the after a right left rotation or after RL rotation, we get this AVL tree which is now balanced. So these are the all about the rotations of AVL tree. I hope every one of you have understood the definition of AVL tree, properties of AVL tree, what the AVL tree is, what is balance factor, when the imbalance occurs as per the formula of balance factor, and how to form a balanced AVL tree by performing all these four rotations, right? So this is the quick comparison table, LL rotation, RR, LR and RL. So these are the LL means left subtree of left child, RR imbalance, the imbalance occurs due to these reasons. That is, in LL, imbalance occurs due to left subtree of left child. In RR, imbalance occurs due to right subtree of right child. In LR rotation, imbalance occurs due to the right subtree of left child, and in RL rotation, imbalance occurs due to the left subtree of right child. So these are the fixes. In LL, we perform the right rotation. In RR, we perform the left rotation. In LR, left rotation plus right rotation. In RL, right rotation plus left rotation. So the key takeaways are AVL trees guarantee balanced height. That is that AVL tree is a balanced tree ensuring fast operations. Rotations are the core mechanism to restore balance. LL and RR are single rotations while LR and RL are double rotations. That is, we have to perform two rotations in LR and RL, but in LL and RR we need to perform only single rotation, right? So this balancing makes AVL trees more efficient than plain binary search trees, especially for large data sets. Now, third question says that make AVL trees from the following values. So in the second question, I have told you how to make the tree balance, thereby constituting the AVL tree. You can easily make the AVL tree for this set of nodes or this set of values. Let us consider the first set of keys. So let us carefully build the AVL trees step by step for both set of values. An AVL tree is a self-balancing binary search tree where the height difference, that is also known as balance factor, between the left and right subtrees of any node is at most 1. That is, it cannot be greater than 1. If inserting a node causes imbalance, we have to perform any one of these four rotations, like, right? So for the first set of keys, we have been given this set of keys 30, 20, 10 up to 42. So we start inserting from first. So the root node will become 30. Next we want to insert 20 because 20 is less than 30. It will be added as the left child of 30 and tree is still balanced because left height is 1, right is 0, 1 minus 0 is 1. So the balance factor is 1. So up to this tree is balanced. But when we trying to insert 10, because after 20 we are going to insert 10 and 10 is less than 10 is less than 20, 10 will be added to the left part of 20. In this case, when we calculate the balance factor, it will become imbalance. So we have to perform the right rotation at 30 and new node will become 20, left node will become 10 and right node will become 30, as we have discussed already in question number 2. So you can perform all these any one of these four rotations repeatedly to constitute the AVL tree. I hope you have already understood the concept in question number 2, right? So for the first set of keys, the final AVL tree will come out to be as shown in this picture, right? Similarly, we can also constitute the AVL tree for second set of values by following the same method. When the tree becomes imbalanced, that is, when the balance factor becomes either less than -1 or greater than +1, the tree becomes imbalanced. You have to perform any one of these four rotations to make the tree balance. That's why the definition says that AVL is a self-balancing uh, tree, right? So for the second set of values, the final AVL tree will look like this. Clear? So for these two set of values, we have successfully constructed the AVL tree. Simply when imbalance occurs, we have to apply any one of these four rotations, and finally we will be able to construct the final AVL tree by using these rotations, right? So we have solved question number 3. Now we are going to question number 4, that says that define red black tree and explain its various properties. So these are some key takeaways for AVL tree. That is, always insert like a normal binary search tree. You already know that in binary search tree, whenever you are adding a new node, if it is less than the root node, it will be added to the left part. If it is greater than the root node, it will be added to the right child. So that's why uh, we have to first we need to first try to insert the nodes using binary search tree. Then after insertion, we have to check the balance factor. If the tree is imbalanced, we have to make the balance by performing the rotations. So if imbalance occurs, apply the correct rotation. You can apply any one of these four rotations, right? Now we come to question number 4, that is define red black tree and explain its various properties. So red black tree is a self-balancing binary search tree. Again, like AVL tree, red black tree is also a self-balancing binary search tree that ensures efficient operations, that is search operation, insertion operation, deletion operation in big O, log, and time by enforcing specific color-based rules. Each node is either red or black, and these properties guarantee that the tree remains balanced. So a red-black tree (RBT) is a type of balanced binary search tree where each node carries an extra attribute, that is a color. It can be red or black. The coloring rules maintain balance, preventing the tree from becoming skewed and ensuring logarithmic time complexity for operations. These are few of the properties of red-black trees. The structure of an red-black tree is governed by 5 key properties. First property says that node color property, every node is either red or black. Second, the root node is always black. Third, a red node cannot have a red child. This prevents continuous red links and ensure balance. Fourth, every path from a node to its descendant, that is null leaves, must contain the same number of black nodes. This guarantees uniformity in path lengths. Fifth property says that all null leaves are considered black. Why these properties matter? First is balance maintenance. These properties prevents the tree from degenerating into a linked list like a skewed binary search tree. It also ensures efficiency, that is search operation, insertion, deletion operation run in big O of log and time. It also guarantees that no path is more than twice as long as any other path, keeping operations consistent. Comparison with other trees, we can compare the red black tree with other trees like binary search tree and AVL tree. First feature is balance method. In binary search tree, there is no balance method. In AVL tree, we use the balance method. In red black tree, the balance method is relaxed. That is we are using colors. As far as insertion deletion operation occurs, in binary search tree, insertion deletion can occur in big O of n time in worst case. AVL tree takes time big O of log n for insertion and deletion operation, but costly rotations are required. In red black tree, insertion deletion operations are performed or takes big O of log n time, but fewer rotations are required. As far as search efficiency is concerned, search efficiency in binary search tree is poor if it is unbalanced. AVL tree is a self-balancing binary search tree. The search operation is excellent, and in red black tree, searching happens. Search efficiency is good. Binary search tree can be used for simple storage. AVL tree can be used for databases, memory indexing purposes. Red black tree can be used for in compilers or operating system kernels or associative arrays. So these are some of the practical applications. First application is in the operating system, that is Linux kernel. Linux kernel uses red-black trees for process scheduling. In compilers, symbol tables oftenly are dependent on red-black trees. Databases, efficient indexing and retrieval. Networking, routing tables, and memory management. So in summary, red-black trees are compromised between AVL trees, that which follows strict balance, and regular binary search tree where there is no balance. They achieve efficient performance with fewer rotations, making them widely used in real-world systems. The next question is question number 5. Define brute force approach. List its advantages and disadvantages. In algorithm design and analysis, the brute force approach is a straightforward problem-solving method that systematically explores all possible solutions until the correct one is found. It guarantees correctness but is often inefficient for large inputs due to high time complexity. The definition of brute force approach says that it is a general problem-solving technique where every possible candidate solution is generated and tested until the correct one is identified. It does not rely on heuristics or optimization strategies. Instead, it exhaustively checks all possibilities. Brute force approach is commonly used in searching, string matching, combinatorial problems, and cryptography. Advantages of brute force approaches brute force approach are: first advantage is simplicity. That is, brute force approach is easy to design and implement, and it is also the often the first approach when analyzing a new problem. Brute force can be applied to a wide range of problems without requiring domain-specific knowledge. Brute force approach always finds the correct answer if one exists, since all the possibilities are explored. Brute force approach is also useful as a benchmark to evaluate the efficiency of more advanced algorithms. Brute force approach works well when the problem size is small or constraints are limited. There are some demerits also of brute force approach. First demerit is the high time complexity of the time complexity of brute force approach is often exponential or factorial in nature, making it impractical for large inputs. Second disadvantage is low efficiency. Brute force approach wastes computational resources by exploring many irrelevant or redundant solutions. Brute force approach is also not scalable. That is, performance degrades or deteriorates rapidly as input size grows. Brute force approach provides no deeper insight into the problem structure or optimization opportunities. In some cases, brute force can also consume significant memory when storing all possible states. You can compare the brute force approach with optimized approaches or heuristic approaches. On the basis, first aspect is correctness. Brute force approach is always guaranteed to be correct. Optimized or heuristic approaches may depend on heuristics or approximation. As far as complexity is concerned, brute force approach is usually exponential, whereas heuristic or optimized approaches are polynomial or logarithmic in nature. Brute force approach design is very simple, whereas optimized or heuristic approach design requires deeper analysis. Brute force approach has poor scalability, whereas optimized or heuristic approaches are better suited for large inputs. Brute force approach can be used to solve small problems baseline testing, whereas optimized or heuristic approaches can be used to solve real-world large-scale problems. Context in algorithms design and analysis. In academic settings, brute force approach is often taught first because it illustrates the importance of efficiency and complexity analysis. It helps students understand why the time complexity big O notation matters and motivates the development of more sophisticated algorithms like divide and conquer, dynamic programming, or greedy methods. In practice, brute force is rarely used for large-scale problems, but remains valuable for proof of concept, exhaustive testing, and cryptography security analysis. In summary, brute force is a foundational algorithmic approach, that is, it is simple, reliable, and universally applicable, but computationally very expensive. It is best viewed as a starting point in algorithm design, and it is not the final solution for complex problems. Next question is question number 6. Define traveling salesman problem and solve the following salesman problem using the brute force approach. The traveling salesman problem TSP is about finding the shortest possible route that visits each city exactly once and returns to the starting point. For your given four city matrix, the brute force solution shows the minimum cost to reach A to B to D to C to A. So this is the shortest possible route that visits each city exactly once and returns to the starting point with a total cost of 80. The problem statement says that traveling salesman must visit a set of cities exactly once, starting and ending at the same city while minimizing the total travel cost. That is the cost of, in terms of distance, time, or expense. The key features of traveling salesman problem are each city is visited once. The path is a cycle. That is, starting, we again return to the start node. The goal is to minimize the total cost. Whereas the brute force means checking all the possible permutations of city visits and calculating the total cost for each tour. The steps are first step is fix the starting city A in this case, generate all possible orders of visiting the remaining cities, compute the cost of each tour, including returning to A, select the tour with the minimum cost. So this matrix have been given to us. There are four cities A, B, C, D, and first of all, we have to start from the node A or the city A. The possible tours are A, B, C, D, A, B, D, C, A, C, B. So all these tours are we have obtained using the brute force for traveling salesman problem. Out of all these tours starting from A, we are again returning to A, but the lowest cost is 80. So the answer will be A to B, D to C, and C to A, right? So this is the optimal tour. That is path will be A to B, B to D, D to C, C to A, and minimum cost is 80, right? So we have successfully solved the problem. The key insights are brute force is feasible here because there are only four cities. 3 factorial is six possible tours. So there are these are only the six tours you can easily find out. For larger problems where are 20 plus cities, brute force approach becomes very computationally infeasible. It will take large amount of time due to factorial growth. And advanced method like dynamic programming, that is Heldkarp algorithm or heuristics, genetic algorithms and colony optimization are used for large data sets. The next question is question number 7. That is define 0-1 knapsack problem. Solve the following knapsack problem using brute force approach and take the knapsack capacity as 5. And this is the table given to us. We have to define first the 0-1 knapsack problem and we have to solve this knapsack problem where the knapsack capacity is given as 5. Right? So 0-1 knapsack problem is an optimization problem where you must select items to maximize total value without exceeding a weight capacity. For the given dataset and a knapsack capacity of 5, the brute force solution yields a maximum value of 37 by including item 1, item 2, and item 4. Right. So this is the final answer. We'll be solving now step by step. First discuss the definition of 0-1 knapsack problem. 0-1 knapsack problem statement is given a set of items, each with a weight and a value. Determine the most valuable subset of items that can fit into a knapsack of limited capacity. There is a constraint called 0-1 constraint. Each item can either be included, that is 1, or excluded, that is 0. Functional inclusion is not allowed. Objective function is maximize this function subject to these constraints, where W are the weights. So where V are the values of the items I, Wi is the weight of item I, Xi belong to either 0 or 1, that is decision variable, and knapsack capacity. In this case, knapsack capacity is given to us as 5. Right? It is given. Knapsack capacity is 5. That is value of C is 5. So then brute force approach, that is enumerate all possible subsets of items, calculate the total weight and value, and select the subset with the highest value that does not exceed the capacity. Complexity will be big O of 2 raised to power n, where n is the number of items. Now we are going to solve the 0-1 knapsack problem for this given data. And the knapsack capacity is given as 5. Right. Now, we'll be applying the again the brute force approach. So item, if we take item one, weight is 2, value is 12. Weight is 2, value is 12. Item 2, weight is 1, value is 10. Right? Item, we take item 1, 2, and we do not consider item 3. We consider item 4. Why? Because if we add weight 2 plus 1 for the first two rows, 2 plus 1, 3, and the last row 3 plus 2, 3 plus 2, 5. So knapsack capacity is 5. And we this value should be maximum. So 12 plus 10, 22. No, just a minute. Uh, Total weight is 2 plus 1 plus 2, 5. And, and the maximum value will be, obviously, maximum value will be 1, 12 plus 10 plus 15. That is 37. Why are we are not considering this row, third row? Because weight will become 2 plus 1 plus 3. That is 3 plus 3, 6. And it will exceed the knapsack capacity of 5. That's why we cannot consider this third row. And the maximum, the sum of the value should be maximum, such that the knapsack capacity should not exceed 5, and some of these values should be maximum. So we have to consider the item 1, then item 2, and then item 4. So we have successfully solved this problem, right? So the key insights are including item 3. Why we have not included item 3? Because value is however the largest, it can result in a large sum. But when we consider item 3 with item 2, so 3 plus 1, 4, it is okay, 30, but value is becoming 30. That is not the maximum, which is less than 37. 30 is less than 37. The brute force method guarantees the optimal solution, but is computationally expensive for larger data sets. For larger problems, dynamic programming or greedy heuristics are preferred. Right. Now we jump to question number 8. Question number 8 says that justify that Strassen's matrix multiplication is better than normal matrix multiplication with respect to time complexity. So we have to justify that the time complexity of Strassen matrix multiplication is less than the time complexity of normal matrix multiplication, right? So now see, Strassen's matrix multiplication is asymptotically faster than the normal matrix multiplication. Normal matrix multiplication is also known as naive matrix multiplication method because it reduces the number of multiplications required, lowering the time complexity from big O of n raised to power 3 to approximately big O of n raised to power 2.81. So this improvement becomes significant for large matrices, making Strassen's algorithm more efficient in practice for high dimensional problems. So now we can compare both of them, normal matrix multiplication or naive matrix multiplication method with the Strassen's matrix multiplication method. So first aspect is to consider the basic idea. Basic idea behind normal matrix multiplication is, in normal matrix multiplication method, it computes each entry by taking dot products of rows and columns. Whereas in Strassen's matrix multiplication, basic idea is to use the divide and conquer with fewer multiplications. The multiplications per step in normal matrix multiplication are n raised to power 3 multiplications are required for n into n matrices, whereas in Strassen matrix multiplication, multiplications per step required reduces from multiplications from 8 to 7 per recursive step. The time complexity of normal matrix multiplication is big O of n raised to power 3, whereas time complexity of Strassen matrix multiplication is big O of n log to the n7 to the base 2, that is approximately equal to big O of n raised to power 2.81. The number of additions and subtractions required in normal matrix multiplication are big O of n raised to power 2, but in Strassen's matrix multiplication, more additions and subtractions than naive method are required. As far as efficiency is concerned, normal or naive matrix multiplication method is simple and it works well for small matrices, whereas Strassen's matrix multiplication is faster for larger matrices due to reduced multiplications. Normal matrix multiplication or naive matrix multiplication method is preferred for small scale problems, whereas Strassen's matrix multiplication is used in large scale computations like graphics or machine learning or scientific computing. Right. So why Strassen's algorithm is better? Because the number of multiplications get reduced in Strassen's. So in normal algorithm requires 8 multiplications for each recursive step, whereas Strassen's algorithm cleverly reduces the number of multiplications to 7, trading multiplications for additions. Since multiplication is computationally more expensive than addition, this reduction yields a faster asymptotic runtime because number of additions in Strassen's multiplications are large, but number of multiplications are less. Because multiplication is computationally more expensive than addition, that's why reduction yields a faster asymptotic runtime. Next is time complexity advantage. Normal method time complexity is big O of n to the power 3, whereas Strassen's matrix multiplication method is having time complexity of big O of n to the power 2.81. For very large n, the difference is substantial, especially in applications like machine learning, image processing, and scientific simulations where the matrices can be thousands by thousand in size. Third reason why the Strassen's algorithm is better is the divide and conquer strategy. Strassen's algorithm recursively breaks down matrices into smaller submatrices. This recursive structure allows faster computation compared to straightforward row column dot product method. The trade-offs and limitations are overhead of additions. Strassen's matrix multiplication algorithm requires more additions and subtractions, which can make it slower for small matrices. Numerical stability, it may introduce rounding errors in floating point arithmetic. Practical use cases, best suited for Strassen matrix multiplication method is best suited for large matrices where the asymptotic improvement outweighs the overhead. Conclusion is for small matrices, the normal or naive matrix multiplication method is often preferred due to simplicity and lower overhead. For large scale matrices or large scale problems, Strassen's matrix multiplication algorithm is superior because of its reduced time complexity makes computations significantly faster. In modern computing, Strassen's algorithm laid the foundation for even faster algorithms like Coppersmith-Winograd and subsequent improvements. But it remains a key milestone in demonstrating that matrix multiplication can be done faster than big O of n to the power 3. Let us solve now the question number 9. That is apply quicksort algorithm to solve the following numbers by showing all the steps in computation. So we have been given these numbers 10, 5, 20 up to 15. We have to apply the quicksort algorithm to sort these numbers in ascending order, right? So all right, let us go slow down and go step by step with the actual algorithm. So you can see exactly how quicksort works on your numbers. I will show the algorithm rules and then the array changes at each stage. So the quicksort algorithm pseudocode is like this. It takes three parameters, A, low, and high. If low is less than high, then pivot index is will be given by the partition algorithm, which is here. This is the partition algorithm. It again takes three parameters, A, low, and high. A high will become the pivot. Value of I will be low minus 1. Then there is a for loop. For j is equal to low to high minus 1. If this condition is satisfied, if aj is less than equal to pivot, then 1 is added into value of I and ai and aj are swapped. After that, we will come out of the if statement and also we come out from the for loop. And after that, ai plus 1 and ai are swapped. And finally, I plus 1 will be returned as the result of partition algorithm, right? So partition algorithm will return this I plus 1 value and the pivot index will become I plus 1, right? Because partition algorithm is returning I plus 1. Then this quicksort will be applied again and again recursively to find out in order to sort the given numbers, right? So as you can see here, let us first of all explain this quicksort algorithm for your convenience. If low is less than high, that is this statement, we have to call the partition. This rearranges the array around a pivot. It will recursively call. As I have said, we will be calling this quicksort algorithm again recursively. That is, quicksort will call itself. Recursion. It will use recursion property. Quicksort algorithm will call itself in these two statements. Clear? So recursively call quicksort on the left side of the pivot. Then the second statement is calling recursively quick sort on the right side of the pivot. Partition algorithm, with the partition algorithm, we can choose the pivot. That will be the last element, that is A high. I will be low -1, and then we'll be following these rules. That's now. Let us apply this quick sort algorithm to this set of numbers. Now, pivot will become 15. Why? Because value of high is 1, 2, 3, 4, 5, 6, 7. Value of high is 7. That is at seventh position. This is the value of high. The value is 15. The pivot will become 15. As you can see here, pivot is equal to A high. That is the last element is always again always the pivot. So value of pivot is 15. Okay. Now we have to compare each element with 15. As you can see here, we have to compare each element with this pivot, this statement, this if statement. And if uh, let us explain. So let us compare this 15 element with each element. First element is 10. Compare 10 with 15. Because 10 is less than 15, it will result in swap operation. 10 is less than 15, it will result in swap operation. So this algorithm says that swap AI with AJ. What is I? Low -1. Right. Just a minute. We have to swap AI and AJ. Value of J is low, that is AJ, and I will be low -1. Just a minute. Mm, Finally, swap pivot 15 into place. Result will be 10. Just a minute. Mm. So, let us discuss this alternate explanation. So, the numbers given to us are 10, 5, 20, 217, 315. Obviously, we have already chosen the last element 15 as the pivot. So we have to partition around this pivot element. So the elements, first of all, we have to choose those elements according to the algorithm that are less than 15. So in these, the elements less than 15 are 10, 5, 2, and 3. 10, 5, 2, and 3. And elements greater than 15 are 2017. 2017. So pivot will remain at the middle, and the element lesser than this pivot 10, 5, 2, 3 will become this. So after partition, that is after calling this algorithm, that is the partition algorithm, calling this algorithm partition, calling this algorithm from here to here. Clear? So actually this partition algorithm will result into this. Will result into this result, right? This result. Now we jump to step number 2. Step number 2 is sort the left sub-array. Now we'll be applying the quick sort recursively to this left array, right? So left array contains now 10, 5, 2, and 3, right? Now pivot will again become the last element. Last element is 3. Now again we'll be using the partition algorithm. The elements lesser than 3 in this are only 2. And also we have to take the element yes, so we have to partition around the pivot 3, and elements less than equal to, okay, element less than equal to 3 will be 2 and 3, because in this case we have to take 3 also into inclusion, because uh, pivot is 3, we have to sort the left subarray. uh, so the left subarray will now become 2, 3. The elements which are greater than 3 are 10 and 5, 10 comma 5, right? So now step number 2a, again we'll be sorting now this 2, 3. because the array should contain at least two elements. That's why we have to include three in this case also. So now, as you can see, when we are sorting 2 and 3, these are already in sorted order. So we do not uh, require to apply some partition algorithm again in this case. Now we jump to the right subarray. Right subarray is, sorry, now right subarray is 10 comma 5. We will be coming to this now later on. First of all, we are focusing on this, right? So 2, 3 we have already sorted. Now we go to 10 comma 5. So 10 comma 5 element less than equal to pivot will become the last element, that is 5. So less than equal to 5, only 5 is there, but we have to greater than 5 is 10, but the array should contain at least two elements. That's why we have to consider 5 and 10 into the array. Clear? So step number 2b so successfully sorted. So the left subarray is now sorted. 2 comma 3 comma 5 comma 10. So we have successfully sorted this left subarray. Now what we have to do? Now we have to sort the right subarray. Again applying recursively the quick sort algorithm here. So the right subarray is 20 comma 17. Right? 20 comma 17. Again the pivot element will be the last element, that is 17. Again apply the partition algorithm as per the pseudocode, the algorithm of the quick sort, right? So less than 17 are 17. Less than equal to 7, the pivot element 17 is 17 itself. Greater than 70 is 20. So but we have to include two elements, at least two elements in an array, and we sort now 17 into 20. So the right subarray is now also sorted, and in between the what was the element in between this? It was the 15. So when we apply now the in the step 4 we combine everything. When we combine everything, now we get the final sorted array. So in this manner you can apply this quicksort algorithm recursively, where we have to also apply this partition algorithm to partition the given array into two parts, right? And we have to apply this recursively again and again to sort first left subarray, then right subarray, then you have to combine the result. So we get the final result by applying this quicksort algorithm, right? So I hope you have understood the basic idea behind the quicksort algorithm and behind the partition sub algorithm, which is the part of this quicksort algorithm. And quicksort is calling recursively itself. So it is using the recursion, right? Now we uh, trying to solve the next problem. So this is quite complex. This explanation is quite complex. You can follow this explanation. So that's why I have given two explanations, right? Let us see. Yes, this is the second detailed explanation you can follow, which I have explained to you, right? First is quite complex. You will not be able to understand first. So alternatively, you can follow this detailed explanation, second alternate explanation by applying the partition and quicksort algorithm, right? Now we are going to solve the next problem. That is the question number 10. Question number 10 says that apply the merge sort algorithm. Now we have to apply the merge sort algorithm to sort the this list of numbers. Again, we have to sort in ascending order and we have to show all the steps. First of all, this is the pseudocode of the merge sort algorithm. This is very simple algorithm. In this case also, the merge sort is calling itself recursively here, right? And it uses an algorithm called merge also. Earlier, quicksort were using partition. Merge sort is using merge, right? These are the simple algorithmic steps which you can follow to sort the array. But I will be explaining the uh, sorting, sorting very in a easy manner. What this algorithm is doing? You can substitute the values of left, right, and a and mid. You all know, right? But I will telling you how does the merge sort work by sorting this given array 9 comma 9 comma 5 comma 12 comma 2 comma 7 up to 6. So merge sort, as the term itself speaks, as the term signifies, as the term indicates, we have to split first of all we have to first of all split the given array into two equal halves. So this array contains 4 plus 4, 8 element. So first we split into two parts. First left array will be 9, 5, 12, 2, and right will be 7, 3, 11, 6. Now we have to sort the first left half first. Again, you will be splitting the left half into two halves. It will result in left 9, 5 and right 12, 2, right? Now, now when we reach up containing the only two element, then you have to sort this. How will be sorting? You will be splitting 9 and 5 and then you will be merging. First of all, you have see how will be sorting. Again, we have to carry the splitting operation until we are having a single element in an array. We have to split the given arrays into half and half and half until we are left only with a single element. So we have again divided this array 9, 5 into two equal halves, and we are getting only one elements in each of these two arrays. That is, first array will contain a single element 9 and second 5. Once we have splitted these arrays into containing only one element, then we will be merging. So when we are merging 9 and 5, these will be sorted, right? These will be sorted, that is in ascending order 5, 9. After that, we'll be applying the same operation in 12, 2. We will split 12, 2 into two equal halves, that is 12 and 2. Then we'll be sorting 2, 12, right? Just a minute. By mistake, I have pressed some button. So see now here. See now. Now, after we have sorted this 5, 9 and 2, 12, now we have to apply. See, when we have splitted 9, 5 into two arrays containing only single element, you have applied the merge operation. And this merge operation is nothing but this merge operation. Simply, we have to substitute the value of left, right, and A. What is left? What is left? Left is this. For example, when you are merging, okay. So left and right, you know, this is the left part and this is the right part, left and right. And A is the given array, which you have to sort. So this is the that merge operation, right? And merge sort operation, merge sort will be applying to left and then right part, right? So you can substitute the values of left and right, and then we have successfully sorted 5, 9 and 2, 12. Then we get these two arrays 5, 9 and 2, 12 in sorted order. Then we will be merging these two 5, 9 this array and 2, 12. And when we trying to merge these two 5, 9 and 2, 12, first of all we will be comparing 5 and 2. Clear? So because 2 is lesser than 5, we take 2. Then we compare 5 and 12, right? We'll be comparing each element of the first array with the each element of the second array. So we are comparing 5 and 2, we take 2. 5 and 12, lesser is 5, so we take 5. Then we compare 9 with 2. Clear? 9 with 2, compare 9 and 12. Compare 9 and 12, and lesser is 9, we take 9. Right? 9 and 2. Okay. So remaining is 12. Clear? 9 and 12. Okay. So result will be, we have to sort this in. It will merge operation will, when we will applying the merge on these two sub arrays, the merge operation will result in the sorted array, that is 2, 5, 9, 12. So these comparison operations, are nothing but the result of these comparison, that is calling merge. That is the That is the this comparison, this if statement. Clear? This is the if statement to compare where we are doing the comparison, right? So this is the simple logic behind merge sort. That's why the name merge, because we are merging the arrays and sorting them in ascending order. So we have got this result up to now 2, 5, 9, 12. Now we have successfully sorted this array. Which array? This array 9, comma 5, comma 12, comma 2. Then we have to solve this right part 7, 3, 11, 16. 7, 3, 11, 16. Now again we'll be splitting this array into two parts, that is 7, comma 3 and 11, comma 6. Left part will be 7, comma 3, right will be 11, comma 6. Then we have to split again 7, comma 3, that is into 7 and 3. Then we will be merging these two 7 and 3 in ascending order 3, comma 7. Then we will be splitting 11, comma 6 into two subarrays containing single element 11 and 6. Then we will be merging these 11 and 6 in ascending order 6, comma 11. After that, we will be applying merge operation on 3, comma 7 and 6, comma 11, right? Which will result in this sorted ascending order. Now we have obtained two arrays in sorted order. First is 2, comma 5, comma 9, comma 12. Second is 3, comma 6, comma 7, comma 11. When we applying merge operation on these two, that is 2, comma 5, comma 9, comma 12. 2, comma 5, comma 9, comma 12, and second is 3, comma 6, comma 7, comma 11, right? So again we'll be comparing these elements according to this merge algorithm. So you know, according to this merge algorithm, this is the merge algorithm. Let me tell you, so you can easily apply this merge algorithm. So this is the comparison operation in the merge. When you compare, when you apply this comparison operation, this is the simple logic where you are sorting, right? Based on this comparison by calling the merge algorithm. Now, what are left and right? What are left and right? So, as you can see here from these are nothing but left and right arrays. You can see here these are left and right are two arrays. For example, in the given when we have splitted the we need to sort this array, right? So when we have splitted this array into two halves, so obviously this is the left and this is the right. So I think now you have understood what are left and right. Left is nothing but left array. When we have split it, as you can see, we are dividing the length of the array by 2. Why we are dividing by 2? Because we are trying to split the given array into two parts: left array, left subarray, and right subarray, right? So left hand, when you are applying, on which you are applying the merge operation. I have earlier told you on which left subarray on the right subarray, and A is the given original array. A is the given original array. So this is the given array. This is the given array, capital A. And we when according to this logic, according to the logic of merge sort, we divide the length of the given array by 2 in order to get the left array and right array. And furthermore, we will be recursively applying this merge sort algorithm. Merge sort will call itself. We are using recursion. Why? First on left and then on right. You can easily see here when you have splitted the given original array into these two subarrays, left subarray and right subarray, then you are again applying the merge sort on this left subarray, that is 9, 5, 12, 2. You can easily see you are again dividing this array into two parts, but left subarray and right subarray. So you are again splitting these into two halves using this logic. Using this logic, you are applying the merge sort algorithm recursively again and again. Merge sort is calling itself again and again on the left subarray and the right subarray. And this is the logic for merging, where you are merging two arrays and sorting them in ascending order. How will you sort them in ascending order? Based on this comparison operation. Based on this comparison operation, which I have highlighted here, right? So you have to simply substitute the value. This is only the algorithm. I have explained the idea and logic behind this merge sort algorithm to you, as we have done in quicksort, right? So because of the time issues, I am not substituting the values of all these variables I, j, k, and so it will take large amount of time. You have to remember this algorithm, and you have to remember the logic and idea behind this algorithm. How the merge sort is, what the merge sort is doing, what the merge operation is doing. That is what does this merge sum algorithm is doing. I have explained this idea to you. Clear? Now simply you have to substitute the values. You will be able to find out the sorted array. So the final sorted array, the final result that come after applying all these merge sort and merge algorithms will be this. That is, this is the final sorted array after applying the merge sort and merge algorithms. Right? Merge algorithm is the part of the merge sort algorithm. As earlier, partition algorithm was the part of the quicksort algorithm. Right? So in summary, what we have done so far in merge sort, we have first is the divide until single element, which I have earlier told you. We have to divide the given original array again and again into two halves until we get the array with a single element, right? Then after dividing, you merge back, vice versa, reverse operation. First you have divided, then you are merging. And why you are merging? After merging, you are sorting them in ascending order using the comparisons. I have earlier told you comparison operation. Then each merge step builds a sorted list. So finally we get the sorted list from two halves, right? So this is the simple solution to sort the given array in ascending order using the merge sort algorithm, right? Now the next question is question number 11. Question number 11, which says that now we have to sort the given numbers using the heap sort algorithm. So this is a very simple algorithm, right? So heap sort algorithm. So perfect. Let us write the formal pseudocode for heap sort and then apply it step by step to your given array. Given array is 10, 5, 20, 2, 17 up to 15, right? So this is the given array. We have to sort these numbers using the heap sort. Clear? So this is the pseudocode or the algorithm for heap sort. Now this heap sort, this is the main algorithm heap sort, and it uses again another algorithm which is called build max heap. You already many of you know that how to build a max heap. Max heap. So let me explain to you. This heap sort algorithm is using two sub algorithms. First is build max heap, which is used to build a max heap, and second it is using the max heapify. Max heapify is used by build max heap algorithm in turn. So this is the another algorithm which is being used here, max heapify. Clear? So now let us understand how to. First step is what? In the first step in heap sort is what? First step is to build a max heap. And what is A? A is the given array which we need to sort in ascending order, right? So the given array is 10, 15, sorry, 10, 5, 20, 2, 17, 3, 15. So transform into max heap. So what is a max heap? Where the how will you form the max heap? Just a minute. Let me explain you. So how to build a max heap? See, arrange elements so that each parent should be greater than children. The value of the parent can be equal, but it can be the value of the parent should be greater than or equal to its children. So if you trying to make this largest element ends up at the root. So the root node will always have the maximum element. So largest element will be ending at the root. So root node will always be having the uh, largest element. So you have to property max heap has a property that the value of the parent should always be greater than equal to the value of the parent should always be greater than equal to children. Okay. So you can easily build this max heap using for this given array. The build max heap operation will result in this max heap, right? This is the max heap. You have to simply trying to make a heap. Remember that the parent should value of the parent should always be greater than equal to its children, right? So you'll be able to build a max heap like this, right? Now after building the max heap, after building the max heap, you have to next step is for loop for I is equal to length a down to 2 and swap a1 with ai. Heap size is decremented by 1 and then you have to apply this max cp5. Let me again, you can substitute the values. You can substitute the values, but let me tell you the basic idea or logic behind the heap sort. So first of all, how many elements are there? 1, 2, 3, 4, 5, 6, 7. So sort iteratively. I is first of all I is 7. Swap the root element with the last. First of all, we have to swap the root element. So root element largest value occurs at root. As I have earlier told you in max heap. In max heap, the largest element always occur at the root. And in when you build a max heap, the value of the parent should always be greater than equal to its children. So first of all, first step says that swap the root element with the last element, which is the 10. So 10 will take the place of 20, 20 will take the place of 10, right? So we will get this array, right? Then the what you have to do now? You have to now perform this heapify operation. You have to perform this heapify operation. Now what this heapify operation is saying? Clear? Let me explain. Repeat until array is sorted. Swap root with the last element in the heap. Earlier told you. Reduce the heap size by 1. Clear? And then heapify the root to restore max heap property. Heapify the root to array sorted in ascending order. So let us discuss in detail. First of all, we have to build the max heap. As you can see here, this is the given array. Let me start with from scratch. You can follow the explanation from this first step. You have to build the max heap. Max heap is this because you can check here. This is the why this is the max heap. How we have constructed this max heap? By adding these, which we will be starting the trying to start these elements from the first. First we add 10. Okay, 10. Then we are having 5 because 5 is less than 10. 5 is less than 10. It is okay. 5 can be added to the left part of 10. Then 20, but 20 is greater than 10 and 5. So 20 will be the parent because in max heap the value of the parent should always be greater than equal to children. So when you apply the max heap, when you build the max heap, we will get this max heap. As you can see, we can check the property of the max heap in this case. The value of the parent here, 20 is greater than its children, that is greater than 17 and 15. In this left subtree, 17 is the parent for 2 and 5. So value of parent is again greater than its children 2 and 5. 15 is again greater than 3 and 10. So this is the max heap, right? So you have successfully built the max heap. Now you have to apply you have to extract the maximum element and then you have to apply the heapify, right? So first as I have earlier told you, you have to swap root element 20 with the last element. Last element is 10 and the root element is 20. So you have to swap this 20 with 10. So 10 will take the place of 20, 20 will take place of 10, right? Then you have to apply the 1, 2, 3, 4, 5, 6, 7. Then you have to apply the heapify operation, right? Heapify operation says that first you have swapped the root, that is largest element with the last element in the heap. Then you have to reduce the heap size by 1 and heapify the root to restore max heap property, right? So okay, so you have to reduce the size of the heap by 1. So 20, you don't need to consider 20. Remaining element, again you have to build the max heap on on the remaining. So in this case, highlighted portion is the max heap. Now you have excluded this 20 element, right? The highlighted portion is again the max heap. So you have to again now what you have to do now? Now you have to again swap the root element 17 with the last element. Last element is 3. So 3 will take place. Now take the place of 17. 17 will take place of 3, right? So now you have to again reduce the size of the heap by 1. So you have now excluded 17 and 20. The remaining elements are these. Now you have to again build a max heap on these highlighted elements. So by applying max heap, by building max heap on this element, we get this max heap, right? Because we have excluded these two elements, 17 and 20, because the size of the heap is again reduced by 2. So now this we got this max heap, right? Now again we'll be iteratively we will be again swapping now 15 with last element, which is 5. So 5 will take place of 15. 15 will take place of 5, as you can see here. 15 comes here and 5 comes here. So now we will be excluding. Now again we'll be reducing the size of heap by 1. Again 2 elements were excluded. Now 3 elements will be excluded. That is, now we do not need to consider 15, 17 and 20. Now again we apply the what max heap. Again we apply the max heap. Again we build the max heap. So this we again build the max heap for these elements 5, 10, 3, 2. So max heap obtained is this highlighted. This is the max heap obtained. Now what we'll do? Again we will be swapping the first element, root element, largest element with the last element. Last element is 2 and the root element is 10. So 2 will take the place of 10. 10 will take the place of 2. So 2 will come here, 10 will come here. Okay. Now again you will be reducing the size of heap by 1. So he will now contain only 3 elements, 2, 5, 3. Again we will be making a max heap on 3 elements. This is the max heap obtained, highlighted. This is the max heap obtained. Again, what we will do? These elements we do not need to consider 10, 15, 17, 20. Now again, we will be swapping 5 with 3. So 3 will take the place of 5. 5 will take place of 3. So 3 will come here and 5 will come here. Again, reduce the size of the heap by 1. And again, now build the max heap for these two elements 3, 2. Again, the max heap will remain these two elements, because max heap says that the value of the parent should always be greater than his children, right? So now what will we do? Now again, now we are now left with only two elements 3, 2. Again we'll be swapping 3 by 3, swapping the first root element with the last element. Last element is 2 and the largest element at root is 3. So swapping 2 and 3, 2 will take the place of 3, 3 will take the place of 2. So we get right. So we get the elements 2, 3, right? And remaining elements will remain as it is. 2, 3, 5, 10, 17, 15, 17, 20. So the given numbers are sorted using the heap sort, right? So I have explained only the idea behind the heap sort. Simply, this is only the algorithm. This is only the pseudo code or the algorithm where we have to only substitute the values. You are now you are having sufficient expertise to substitute the values of those variables if you are given some algorithm or program, right? So in this heap sort, we have to substitute only the values, right? You substitute the values and apply this algorithm, and you will be able to sort the given array using the heap sort. I have only explained the idea and logic behind the heap sort to sort the given array in ascending order, right? So we have successfully sorted the given array using heap sort also. So we have discussed almost all the algorithms. Now we jump to question number 12. Question number 12 says that write an algorithm for quick sort. We have already done so. We have already discussed quick sort. So nonetheless, for the sake of completeness, let me show you answer to question number 12. Question number 12. So I have already explained the quicksort algorithm with an example how to sort a given array in ascending order using the quick sort. So again, the same algorithm is there. That is quick sort, applying recursively, and the partition. Partition, quick sort algorithm is also making use of the algorithm partition. Clear? So I think I think that I do not need to repeat it again because we have already discussed with an example how the quicksort algorithm works. Like, right? So this is the quicksort algorithm. Same algorithm which we have already discussed. An example, another example has been given here, right? And the detailed explanation you can see. Detailed explanation you can see, right? This is the detailed explanation. Explanation. These are the complexity given. Sorry, this the time complexity of quicksort in best or average case is big O and log n. This is not division. This is wrongly written. This is this backslash you have to remove. The time complexity of quicksort in best and average case will be big O of n into log n only, right? So you have to here is again there is a mistake. You do not need to consider this backward slash. The space complexity of quicksort is big O of log n only, right? Question number 13, that is merge sort. Merge sort we have already discussed. Question 13, merge sort, you can again, so the same algorithm is there. Same algorithm that is making use of merge sort recursively, then applying the merge operation. So merge sort, what was the first step? Dividing the array into two halves. Then you go on dividing the given arrays into two halves until we remain with the single element in array. Then we start merging and sorting, right? So same merge set algorithm with an example we have already discussed, right? So this is another example solved using the merge sort, right? You can see. Now the next is question number 14, heap sort. Heap sort we have just discussed, right? Now we jump to question number 15. Now we jump to question number 15. So write an algorithm for binary search. It is very simple. All of you must be knowing, for nonetheless, for the sake of completeness, let us revisit the what is binary search algorithm. Binary search. Binary search is a classical divide and conquer algorithm that searches for a target element in a sorted array in big O log n time. It repeatedly halves the search interval until the element is found or the interval becomes empty, right? So this is the binary search algorithm. Again, you have to substitute the values at your own. Let me explain the idea. For example, this is the example. So this is the given array. We have to search the element 15 within this array by applying the binary search. So what will we do? The value of low is 1, high is 7. Low, while low 1, that is the first element. First element that is low, and the last element 1, 2, 3, 4, 5, 6, 7. So the high is 7 because the last element 25 is positioned at number 7. So high is 7. The first element 2 is positioned at number 1 position. So low is 1, right? Then we compute the mid value. 1 plus 7 divided by 2, that is 8 by 2. Floor value we will take. That is 8 by 2, 4. And at fourth position, 1, 2, 3, 4. A4 is 10. Since 15 we want to search, 15 is greater than 10. So we will go to the right half. We will go to the right half. Mid is 4, A4 is 10. So this is the mid. We have successfully find out the middle element, that is 10. So because we need to search 15 and 15 is greater than 10, so we will go to the right part of 10. As you can see, 15 lies on the right part of 10. Again, now the new bound will become, low will become what? 1, 2, 3, 4, 5. 15 is in the right part. The low is at position 1, 2, 3, 4, 5. Low is 5, 25. Last element is at again at 7. Again we will take the floor value, mid value. So 5 low plus high, 5 plus 7 by 2, it is 6. So at 6th position, 1, 2, 3, 4, 5, 6. At 6, we are having 20. So this is the now this becomes the middle element 20, but we need to search 15. 15 is less than 20, so we will go to the left subarray, right? So now we are only left with this single element. Low is also 5 and high is also 5 because 15 is at positioned at 5. So mid is 5, A5 is 15. So match is found. We have successfully searched for element whose value is 15, right? By applying the binary search algorithm, simply you have to substitute these values. This is the pseudocode or algorithm for binary search. Uh, it will result in the same result which we have solved now for the given example, right? Now we are going to solve the problem number 16. Analyze the time and space complexity of the following algorithm in best, average, and worst cases, right? Question number 16. Question number 16. Let me complete this binary search first. Again, this has been written wrongly. This backward slash will not be there. The time complexity of the binary search will be big O log n comparisons. Space complexity will be big O of 1 for iterative version. Again, this backslash will is an error. You have to ignore this. The space complexity of binary search is big O log n for recursive version, and it works only on the sorted arrays. Binary search, remember, binary search always works on the sorted arrays. As you can see, this is the sorted array. All the elements are already sorted in ascending order. So binary search always applies on sorted arrays, right? So why binary search is efficient? Binary search is much faster than linear search for large data sets. For example, if we want to search in an array of size 10 lakh, so if you are having 10 lakh element, linear search will take this number of comparisons, but binary search will take only this number of comparisons. That is, again, this is had been written as wrong. It will be log to a log, base will be 2, and this is quantity 10 lakh or whatsoever is. So it will result in only 20 comparisons. Linear search takes so much comparisons that is equal to the number of elements in the given sorted array, whereas binary search will take only 20 comparisons, right? Why 20? How we have computed 20 comparison? Log base will be 2 and value will be this. So the result will be log. It will result in value 20. So 20 comparisons are needed only to sort this number of elements. So that's why binary search is efficient than linear search. Binary search is very much faster than linear search. So in summary, binary search is a logarithmic time algorithm that has this search space at each step. It is found that the number 15 we have found in the given example, we have searched for the value 15 only in 3 steps, right? Now, the next question is question number 16, that is analyze the time and space complexity of the following algorithm in best, average, and worst cases. Quick sort, merge sort, heap sort, binary search. We have to compute the time space complexity for all of these. So here is a clear breakdown of the time and space complexity of all these algorithms in best, average, and worst cases. Quick sort can degrade to big O of n raised to power 2, while merge sort and heap sort consistently perform at big O of n log n. Binary search is highly efficient at big O log n but requires sorted input. So this is the comparison you can see. For example, let me explain. Quick sort in best case takes big O of n log n time. In average case, quick sort takes big O of n log n time. So, and quick sort in worst case takes big O of n raised to power 2 time, right? So, quick sort space complexity in best case is big O of log n. Space complexity of quick sort in worst case is big O of n. So, you can refer to this table to quickly analyze the time and space complexity for each of these algorithms. That is for quick sort algorithm, merge sort, heap sort, and binary search algorithm, right? And you can refer to this. Refer to why this how this time and space complexity is we are getting. You can go through this detailed analysis at your own. I have explained in very clear terms why the complexity of these sorting algorithms are these and these as per this given table in best, average, and worst case. You can read it at your own because the video is getting large today. So you can read it and on. You can analyze the time and space complexity at your own in best, average, and worst case, and you can refer to this table if you want to remember the time and space complexity of each of the algorithms in best, worst, and average case, right? This is the detailed analysis. You can read it at your own, right? How these complexities are being computed, right? So this is the analysis. You can read it at your own, right? Now, So the you can read this is the key takeaways are quicksort is the fastest algorithm. If somebody asks you, tell me the fastest algorithm fastest algorithm you have read so far. So quicksort is the fastest in practice, but quicksort is risky without good pivot selection. If the pivot is not selected cleverly, then there is a risk in quicksort. Merge sort is stable and predictable, and it is ideal for linked list and external sorting. Heap sort guarantees big O of n log n time but is less cache friendly than quick sort. Binary search is optimal for searching sorted arrays but useless on unsorted data. If the given array is unsorted, you cannot apply the binary search. It will be very result in very large complexities. Right? Now we jump to question number 17. 17 question number says that define the term algorithm and write its characteristics. So algorithm is a finite sequence of well-defined instructions designed to solve a problem or perform a computation. Its key characteristics include clarity, finiteness, defined inputs and outputs, and effectiveness. The formal definition of algorithm can be algorithm is a step-by-step procedure or a set of rules for solving a problem in finite number of steps. The purpose of the algorithm is to provide the logic or the solution to a problem, which can later be implemented in different programming languages. So these are some of the characteristics of an algorithm. Algorithm accepts zero or more input values which must be clearly specified. Algorithm produces at least one output which is the solution to the problem. Clear? Algorithm must terminate after a finite number of steps. It cannot run indefinitely. Each step in an algorithm must be clear, unambiguous, precisely defined. Unambiguous means there should not be any confusion. Steps in a algorithm should be simple enough to be carried out using basic operations within a reasonable time. Clear? So this is an example of a sorting algorithm. The key takeaways are algorithms are the backbone of a computer science, forming the basis of programming, artificial intelligence, and data analysis. Algorithms ensure efficiency, reliability, and scalability in solving problems. Right? So, next question is question number 18. Question number 18 says that explain various asymptotic notations and their properties. So, you already know there is a notation called big O notation, that is upper bound. Big omega, big O is written as O. Big omega is written as omega, which we have read in physics. Big theta is written as theta. Little o is written as little o. So these meanings of these asymptotic notations are given, and these are the definitions. That is in terms of equations, and their usage is when these notations can be used. In which case, for example, big O notation can give you a worst case performance. Big omega best case performance. Right? And these are the properties of the asymptotic notations. These are the properties of a asymptotic notations. You can refer to. You already know this. What is reflexivity, symmetry, transitivity. So you can read it at your own. These are the properties of the asymptotic notations. Right. These are some of the practical insights. That is, big O is most commonly used in algorithmic analysis. That is in sorting algorithm. That is merge sort. For example, big O merge sort complexity is big O of n log n. Big omega is useful when proving lower bounds. That is comparison based sorting requires at least big omega n log n. Big theta gives the more precise characterization. Binary search is having an complexity of theta log n. Right? These are some of the risk and misinterpretations. Right? You can read it at your own. Risk and misinterpretations. So in summary, big O, omega, theta are core notations for algorithmic analysis. So now we jump to question number 19. Explain various types of problems and also explain various problems solving approaches to solve these problems. So these are some of the problems. You can read it at your own. First category of problem is known as optimization problem. The goal of these problems is to find the best solution among many feasible ones. Example are shortest path, Dijkstra algorithm, minimum span in tree, Kruskal algorithm, Prim's algorithm. Second category of problems is decision problems whose goal is to find the answer in terms of yes or no. Example is graph, whether a graph is a bipartite graph or not. Does a subset of a set sum to a target or not? Third category is search problems. So all these are the types of problems. You can read it at your own. This is again a theoretical question. Simple and sober question, right? You can read it at your own. Now we jump to question number So these are the approaches which you can use to solve these different types of problems. You can refer to this table. For example, uh, divide and conquer. Divide and conquer as the name of the approach. You have to break the problem into sub problems and you have to solve those sub problems recursively. And then at the end, you have to combine the result. Example of divide and conquer are merge sort, quick sort, binary search. And divide and conquer approach is best for recursive functions or recursive problems or structured problems. So you can refer to you can refer to this table where you can apply which approach, in which case you can apply which approach, and what are the examples of these example algorithms for these approaches, right? So these are the key considerations in choosing an approach. On the basis of which factors you have to choose an approach. That is on input size, on the base of input size, on the base of problem structure. For example, dynamic programming requires overlapping sub-problems. What are the constraints? Backtracking is useful when constraints eliminate large portions of the search space. These are some of the challenges and trade-offs. Greedy algorithms may fail if the problem lacks the greedy choice property. Dynamic programming can be more memory intensive. It requires a lot of memory. So these are some of the challenges associated. Now we are left with this is the summary. We are left with next question is question number 20. Differentiate between mathematical analysis for recursive and non-recursive algorithms. Clear? So mathematical analysis for non-recursive. Non-recursive algorithms are also known as iterative algorithms. Definition is algorithm that use loops like for loop, while loop instead of self calls because it is non-recursive. Recursive are which call itself. Self calls are recursive algorithm, but these are iterative. Non-recursive are iterative. They do not call itself. Self calls are not included. Clear? So this is an example of simple iterative. You know already what is an iteration. For example, for loop, value of I will vary from 1 to n. So this is an iteration. You already know what is an iteration in for loop, right? Then we come to this is the time complexity of non-recursive or iterative algorithm. Then we come to recursive algorithm. You know what is recursion? That is function calling itself. You can see this in example. Tn is described in terms of again tn by 2. So it is calling recursively itself. So that's why it is a recursive algorithm. This is the analysis of recursive. So you have solved such type of problems using either substitution or recursive master method or master theorem method. I will be telling you in the last question today. So this is the comparison table. You can easily compare non-recursive algorithm with recursive algorithms, right? Key takeaways, you can read it at your own. Now we come to question number 21. 21 says that calculate the time complexity of these cases for all these codes. Code number 1, code number 2, code number 3. Different for loops are given to us. We have to calculate the time complexity. In question number 21, let us solve first part. So in the first part, you can see in the first part, for loop is there. I1, I less than n, I is equal to I plus 5. So now we are incrementing I by 1. And finally, the I is incremented by 5. Sorry, I is incremented by 5 each time because I is equal to I plus 5. So number of iterations are approximately n by 5. That's why the time complexity is big of n only. Second part, I here in this for loop, we are dividing I by 2. So sequence will become n by 2, n by 4, and so on and so forth up to 1. So the complexity will be log to the base, log n to the base 2. So big of log n, right? Third part, we are multiplying I, so I equal to I into 2. So we are multiplying I by 2. So 1, 2, 4, 8, n. Again, complexity will be big O log n because it is proportional to log 2n, right? Now we come to fourth part. In fourth part, we are having two loops. In outer loop, we are incrementing I by 1. In inner loop, we are multiplying j by 2. So in this case, in the inner loop, we are multiplying j by 2. So 1, 2, 4, so on and so forth up to n. So log n. In the outer loop, we are only incremented by 1. So log n. So log n, sorry. In the outer loop, we are only incremented value of I by 1. So that is n. And in inner loop, we are multiplying value of j by 2. So log n. Log base to n. So n into log n. So complexity will be big O of n log n, right? Fifth part. Here only we are having a single for loop. We are multiplying I by I. So I by I, that is 2 raised to power, first of all, I is 2. 2 raised to power 2 is 4. 4 raised to power 4 is, sorry, 2 raised to power 2 is 4. Then uh, value will become 4. I is 4. 4 raised to power 4 becomes, just a minute. We are multiplying, sorry, we are multiplying I by I. So I value, initial value is 2. 2 into 2 is 4. 4 into 4 is 16. 16 into 16 is 256, like this. So 2 raised to power 2 raised to power k, right? This is the we are doing now. So that's why we solve 2 raised to power k greater than log n. So k is greater than log of log n. So complexity is big of log n. So these are the solution to first type of 5 parts. Let us discuss the last part, problem number 6. So here are again 2 loops. In the outer loop, we are incrementing value of I by 1. In inner loop, we are incrementing the value of j. We are multiplying j by 2. Clear? So for inner, we are having log 2n. For outer, n. So n into log n. So complexity is big O of n log n. As we have already solved such type of problem, right? Now we are left with 2 problems. Question number 22. Question number 22. Arrange the following in increasing order. Let me show you the problem statements. However, you have seen in the answer also for the question number 21, right? Now we go to the question number 22. We simply have to arrange these notations in increasing order, that is increasing complexity, right? So this is the, you can read it at your own. The final order will be like such: big of on is less than big of log n, which is further less than big of square root of n, further less than big of n log n, less than big of n square, and so on and so forth. So this is the final sequence. You can read it at your own. Clear? Now we finally reach to final question, question number 23. Define recurrence relation and calculate the complexity. We have to compute the complexity for each of these 7 parts by 3 methods. First method is substitution or iteration method. Second, recursion tree method. Third, master theorem method. Let me quickly grasp this. Let me quickly cover this. Yes. This is the question. We have to we have to compute the complexity for each of 7 parts using 3 methods. First of all, we'll be using the substitution method. So substitution, substitution you already know. Substitution means Tn equal to Tn minus 1 plus C. Value of T1 is 1 in first part. So when you substitute in place of Tn, you have to, first of all, you have to substitute n minus 1 in place of n here. Please listen carefully. You have to substitute n minus 1 in place of n here, because Tn is equal to Tn minus 1 now. So it will become Tn minus 2. You can see here Tn minus 2. So on and so forth. So the final answer will be 1 plus, because C is a constant, 1 plus n minus 1 into C. So complexity will be big O n. Similarly here, you have to substitute n by 2 in place of n. So it will become n by 4. So in this case, you can use the substitution method to get this complexity big O of n log n. You can try the substitution method for all of these. I can show you the solution. You can try it at your own. This is very important topic, that is finding the complexity using these 3 methods. Substitution I have already told you. That is, you have to keep placing. For example, here in place of n, you have to substitute n minus 1. So n minus 1 minus 1, n minus 2. It will become n minus 2. So this is the substitution. You can solve it at your own. Second method is the recursion tree method. Second method is the recursion tree method. So let me first of all show you the solutions for using the substitution for all of these 7 parts. Clear? So this is the solving all the 7 parts using substitution method. You can read it at your own. Let me show you. Third, then fourth part using substitution, then fifth part using substitution, then sixth part using substitution method, then seventh part using substitution method. Okay, and these are the substitution method results for each of these 7 problems, right? So you can easily read at your own and solve it yourself. I have told you the basic idea. Now recursion tree method. Recursion tree method. For example, we try to solve this second problem. Tn equal to 2 plus n. So recursion, what is calling itself? Recursion tree method. So root cost is n. This is the root cost n. Level 1, 2 nodes. Each cost is n by 2. Each cost is n by 2. So total n. Then level 2. So you can refer to the book by Corman to form a first of all a recursion tree, and you can see the solution here. I am not having sufficient time, so that's why you can do at your own using the substitution. I have solved each of these parts using the recursion tree method. So first of all, you can refer to the book by Corman, and you can learn how to draw the recursion tree to solve all these 7 parts using recursion tree method. However, I am showing you the solution of all these 7 parts using recursion tree method, right? You can do it your own. I think this was the first topic covered by your teacher, and you probably will be knowing how to make use of substitution method, recursion tree method, and master theorem to solve all these, to find out the complexity for all these 7 parts. Now we jump to only the last part that is very important, that is the master theorem. Master theorem, we using the master theorem will be solving all these 7 parts. You should only know the master theorem, then you can easily solve all these 7 parts. So master theorem says that Tn is equal to Atn by B plus Fn, where value of A is greater than 1, equal to 1, number of subproblems. B is greater than 1, that is factor by which problem size reduces. Fn equal to cost outside recursive calls. So in every problem, there will be out of these one of these 3 cases will happen. In every 7 parts, you will encounter one of these 3 cases. So if you find Fn equal to big O of this, then you have to, this is the solution, Tn equal to this theta. In case 2, if you in the given problem you are given Fn equal to theta of n to the power log ba, then this is the solution, Tn equal to theta, this is the solution. In the case 3, if in the problem Fn is given this, then this is the solution, Tn equal to theta of Fn, right? Simply you have to substitute the value of a and b, and you can check whether in the given problem these equations are there or not. If any one of these are there in the problem, by substituting the values, then the solutions are given by this, Tn equal to this, right? So this is the master theorem. Let me show you but in some cases master theorem does not apply. In the solution you can see here right rows is there, here master theorem does not apply to the first part. So in the second part, case 2 matches, because Fn equal to, Fn is Tn, Fn equal to 2 Tn by 2 plus n. So here A is 2, compare with this, compare with this equation, compare with this, I am hovering the mouse over, compare with this equation, Tn equal to what? A value of A is 2, value of Tn by B, so value of B is also 2, you can compare, plus Fn is n, so you have to check now these 3 cases. Fn equal to, what is Fn? Fn is n equal to n to the power log ba, what is the value of A and B? 2 and 2, so n to the power log 2 is 1, n to the power 1, so n is equal to n. So case 2 matches here, Fn equal to theta n to the power log ba. So solution is given by Tn equal to theta n to the power log ba log n. So solution will be Tn equal to theta n log ba is 1, so n to the power n log n, so theta n log n. So I have explained you the idea behind the master theorem. Now you can solve each of the 7 parts using the master theorem. You can see to the part 3 and 4, master theorem again does not apply. For parts 5, 6 and 7, for parts 5, 6 and 7, for part 5 case 1 matches. Simply you have to, what you have to do first of all, in the given equation, this is the given equation, you have to compare first of all this equation with this equation, you have to compare. By comparing this equation, you will get the value of A and B as well as Fn. Then you have to check, you have to match with these 3 cases. If any of these cases matches, then this will be the solution. Out of these three cases, only one case will match, as I explained in part number 2. So in part number 5, case 1 matches. Part number 6, case 1 match. Part number 7 also case 1 match. So the solution is given by case 1, that is Tn equal to theta n to power log Ba. You can apply at your own. You can if you are reading at your own, you will understand how the master theorem is applied. And this is the results for each of the 7 parts in the form of a table. With that being said, we conclude all the solutions to the given practice set of design analysis of algorithm subject. Best of luck for your exam, midterm exam, which is going to be held tomorrow. Thank you.